Hello friends, welcome to lecture series on matrix analysis with applications. So, in this lecture we will talk about subspaces. In the last lecture we have seen that what vector spaces are and how can we see that a given set is a vector space or not over a given real field, okay, real or complex field. So, what subspaces are, let us see. Let V be a vector space over the field F and let W be a subset of V. Okay. This V is a vector space over the field F and this W is a subset of this V. Then this W is called subspace of V if W itself is a vector space over the field F with respect to the same operations of vector addition and scalar multiplication on V. Whatever vector addition and scalar multiplication is in V over F, the same vector addition and scalar multiplication we apply on W, which is a subset of V. If it itself a vector space over the same field F, then we say that it is a subspace of V. So, in any vector space V, two subspaces are trivial. The first one is V itself, okay, because V is a subset of V and it is a vector space, and this 0 subspace which is a trivial subspaces of vector spaces V. The subspace this 0 is simply additive identity, you see, and is also called 0 subspace of V. Okay. So, if a set is given to you, okay, if a subset of a vector space V is given to you, and if this W itself is a vector space over the same field F with respect to the same set of vector additions and scalar multiplication, then we say that W is a subspace of the vector space V. Now, how can we show that a given subset W of V is a subspace? So, instead of showing all the properties of a vector space V, if we show these two properties, that is closure with respect to addition, vector addition, and closure with respect to scalar multiplication, then it is sufficient to show that W is a subspace of this vector space V. Now, how can we say this? You see that we say that V is a vector space over the field F if V with respect to plus is an abelian group, okay. Abelian group means first is closure, next is associative, okay. Then identity element, then inverse element, okay, and then commutative. If these property holds with respect to addition, vector addition, then we say that V with respect to addition is a abelian group, and with respect to dot, the first is closure, the second property is 1 dot V is equal to V for all V in V, okay. Third property is alpha plus beta dot with V is equals to alpha dot V plus beta dot V, where alpha beta are in field and V is any vector in V. Next is alpha beta dot V is equals to alpha dot beta dot V, okay, and same as beta dot alpha dot V, okay. And next is alpha dot V1 plus V2 is must be equals to alpha dot V1 plus alpha dot V2 for all alpha in field and for all V1 V2 in vector space V. So, if these property hold respect to addition and scalar multiplication, then we say that V is a vector space over the field F. Now we are taking W as a subset of V over the same field F with respect to same vector addition and scalar multiplication, okay. Now you see if you say these closure is automatically because of this property, the first property itself says that it is closed with respect to vector addition, okay. Now the second property is associative. Since associative holds for every element u v w in V, So, it will hold for a subset of V also. Okay. Now, we have to show the existence of identity element and inverse with respect to addition. Okay. Now, we know that u plus v belongs to W for all uv belongs to W, and alpha dot u belongs to W for all alpha belongs to field and u belongs to W. Okay. Now, if you take alpha equal to 0, say for example, because it holds for every alpha, so it will hold for alpha equal to 0 also, and 0 dot u is nothing but identity with respect to addition. So, that means 0 belongs to W. So, we have shown that existence of identity element with respect to addition. Now, for inverse you simply replace alpha by minus 1. So, minus 1 dot u is minus u, we have already shown. So, that means inverse element with respect to addition also exist. Now, commutativity property holds because this property holds for every uv in V. So, it will hold for a subset also, because subset elements of W are nothing but the elements of V, and this V holds commutative property for every uv in V. So, it will hold for a subset also. So, we can say that W with respect to plus is an abelian group. Okay. Now, we have to show with respect to dot. Now, with respect to dot, closure is automatically satisfied because of the second property. Okay. Now, 1 dot V is V because it is now this property is holding for every alpha. Okay. You see this property is holding for every V in V. So, it will hold for a subset also. Okay. So, we can say that this property hold, and similarly all the remaining 3 properties also hold for W because W is a subset of V. So, hence we can say that if we show that these 2 properties, then we can say that W is a subspace of V, or we can club these 2 properties as two properties alpha dot u plus V should belongs to W for all uv in W and alpha in F. Okay. So, either we have 2 ways to show that W is a subspace of vector space V. Either we show these 2 properties separately, or we can show the single property and we can show that, then we can say that W is a subspace of a vector space V. Okay. So, now let us discuss few examples based on this. The first example is V we are taking as R2 over the real field R. Okay. Now, W which is given as all x y in R2 such that x plus 2 y is equal to 0, and we have to show that W is a subspace of this vector space V. Okay. Now, what is V here? V is entire R2 and field is R. Okay. So, this is something like this entire R2 is simply a vector space V over the real field Okay. Now, W is simply all x y in R2 such that x plus 2 y is equal to 0. So, it is passing through origin when x is 0, y is 0, and when x is minus 1, when x is minus 2 for example, then y is 1, then y is 1. So, it is something this line. Okay. This is x plus 2 y is equal to 0. So, it is of course a subset of this R2. Now, we have to see that whether it is now we have to show that it is a subspace of this V. So, you take 2 arbitrary element in W and alpha in field. So, U is something you can say U is as x1 y1 and say V is x2 y2. Okay. So, this implies x1 plus 2 y1 is equal to 0 and x2 plus 2 y2 is equal to 0 because U V are from W. So, it will satisfy these properties. Now, if it is a subspace, then we have to show that alpha u plus V must be in W. So, take alpha dot u plus V. So, it is alpha dot u is x1 y1 plus x2 y2. So, it is alpha x1 alpha y1. So, here I am taking the usual scalar multiplication, okay, because I am taking R2. So, we have taken the standard addition, vector addition, scalar multiplication, okay, it is x2 y2, and when you add them, so it is simply alpha x1 plus x2, alpha y1 plus y2, again by the standard vector addition, okay. Now, we have to show that this is in W. So, that means we have to show that x, this is x and this is y. So, we have to show that x plus 2y must be 0, then only we can say that this element is in W. So, you can take x plus 2y. Now, x plus 2y is alpha x1 plus x2 plus 2 times alpha y1 plus y2. It is equal to alpha times x1 plus 2 y1 plus x2 plus 2 y2, and it is 0, x1 plus 2 y1 is 0 from this equation and x2 plus 2 y2 is 0 from this equation. So, it is alpha into 0 plus 0, which is 0, and this implies x comma y belongs to W. So, we can say that this x and this y is in W, that means W is a subspace of V. Okay. Now, similarly, if you want to show that this matrix, this vector space we have taken as all m cross n matrices over the real field R, and W is a subset of this V, we have taken as all collection of all symmetric matrices, where A equal to A transpose. And again, if you want to show that it is a subspace of V, so again it is very easy to show. You simply take two matrices A comma B belongs to W. So, this implies A is equal to A transpose and B is equal to B transpose, and we have to show that a matrix C, which is alpha dot A plus B, is also in W. So, that means we have to show that C is equal to C transpose. So, take C transpose, which is alpha dot A plus B whole transpose, which is alpha dot A transpose plus B transpose, and it is alpha dot A plus B because A transpose is A and B transpose is B. So, it is equal to C. So, this implies C is in W. So, we have shown that W is a subspace of this vector space V, because all the matrices which is equal to its transpose are in W, and we have shown that C is equal to C transpose and C is nothing but alpha A plus B. That means W is a subspace of this vector space V. Okay. Similarly, we can show for the third problem also. You take two arbitrary vectors of P2 and try to show that it is closed under addition and scalar multiplication, or you can show that you can take u and v in P2 and you can try to show that alpha dot u plus v is also in P2. Okay. Now, similarly, if you take the next example where we have taken V as a collection of all functions from R into R, and we have considered a subset W of V such that f of minus 1 is 0. Okay. All those functions which vanishes at minus 1, this we are taken as W. So, again in order to show that it is a subspace of this vector space V, you take any two arbitrary element of this subset W and try to show that it is closed with respect to addition and scalar multiplication. Okay. Now, the last example of this slide, that we are taking V as all n cross 1 matrices over the field F. Suppose A be an m cross n matrix over F is a fixed matrix. Then a set of all n cross 1 column matrices X over F such that A x equal to 0 is a subspace of V. Okay. You see that here we have taken W as all x in V such that A x is equal to 0. Okay. Here A is a fixed matrix of order m cross n, and this x is a vector of order n cross 1. Okay. And the collection of all those x, we are claiming that this W is nothing but a subspace of the vector space V. Okay. Now it is easy to show. You see that if you again you take two elements say x1 and y1 in W. Okay. Now of course this set is never empty. This set is never empty because this is never empty because at least x equal to 0 is in the set. Okay. And if it contains a singleton 0, so that is a trivial subspace of V. And if it is not a trivial subspace, so it will contain infinitely many x such that Ax equal to 0, because this is a linear system of homogeneous equations which has either a unique solution or infinitely many solutions. If it is as a unique solution which is x equal to 0, that is a trivial subspace of V, that is automatically satisfied. But if it has an infinitely many solution, then we can prove it in this way. We will assume that x1 and y1 are two elements in W, that means Ax1 equal to 0 and Ay1 equal to 0, and we have to show that a z which is alpha dot x1 plus y1 is also in W. So you take A into z is A alpha dot x1 plus y1, which is alpha dot Ax1, because alpha is a scalar, and it is Ay1, and it is 0 and it is 0, so it is 0. So that means z belongs to W, and hence we can say that W is nothing but a subspace of this vector space V. Okay. So basically to show that this is a subspace, we have to take two cases. First is a unique solution of this. If it is a unique solution, that means trivial subspace. If not unique, that is infinitely many solutions, and the proof follows on these lines. Okay. So in this way we can see that whether a given subset of a vector space V constitute a subspace or not. In this way we can show that it is a subspace of given vector space V. Okay. Now let us consider few more problems based on this. Now here in the first problem we have taken V as R2 over the field R. Okay. Now we have considered W1, which is all x1 x2 such that x1 is greater than or equal to 0. Okay. So what W here is? So in the first example we have taken V as R2 and field as R. Okay. This is the thing, and x1 greater than or equal to 0. This is x1 and this is x2. x1 greater than or equal to 0 means this thing. So whether this half of this R2 will constitute a subspace of this vector space or not. Okay. So you see that if it is a subspace of this vector space, then it must be closed with respect to addition and scalar multiplication. Okay. Now if you take element say 1 comma 2, 1 comma 2 is in W, yes, because W are all those x1 x2 such that x1 is greater than or equal to 0. Here x1 is greater than or equal to 0, so it is in W. And you take, and alpha is any real number, it's come from the field. So if you take alpha as minus 1 says, and minus 1 dot 1 comma 2 will be minus 1 comma minus 2, which is not in W. So that means it is not closed with respect to scalar multiplication, and that means it will not constitute a subspace of this vector space V. Because if it is a subspace of the vector space V, it must be closed with respect to vector addition and scalar multiplication. Okay. So if we have to show that it is a subspace of vector space, then you must show that it is closed with respect to addition and scalar multiplication. And if it is not a subspace at all, then simply give a counter example to show that it is not closed with respect to addition or scalar multiplication. Okay. Now take second example. Now here we have considered all x1 x2 in R2, so x2 is rational. So again when you take W as all x1 x2 in R2 such that x1 is rational, okay, x2 is rational. Okay. Now, again if you take say 1 comma 2, it is in W because here x2 is rational. Now, if you take alpha as under root 2, then under root 2 dot 1 comma 2 is simply under root 2 comma under root 2, which is not in W, because now x2 is not rational. So, it is not closed with respect to vector scalar multiplication. So, that means it is not a subspace of this vector space, not a subspace. Is it clear? Okay. Now, discuss second problem. The second problem is we have taken P as V as P2, P2 are all polynomials of degree less than equal to 2 over the real field. Then which of the following subsets of V are the subspaces of V? The first one is all P in V such that P dash 1 equal to 0. Okay. So, here V are all P2 over real field R, and W we have taken as all P in V such that P dash 1 is equal to 0. Okay. Now, you take two polynomials P1 and P2 in W. Okay. That means P1 dash 1 equal to 0 and P2 dash 1 is also 0, and if it is a subspace then it must be closed with respect to vector addition and scalar multiplication. So, that means you take an arbitrary you take this P, and we have, if it is a subspace then we have to show that it is in, then we have to show that P dash of this P dash of this P at 1 must be 0. So, what is P dash of this? This is alpha dot P dash at 1, suppose, because this implies that P dash is simply alpha dot P1 plus P2 dash, dash means derivative, which is alpha dot P1 dash plus P2 dash. Now, P1 dash at 1 is nothing but alpha dot P1 dash plus P2 dash at 1, and which is alpha dot P1 dash at 1 plus P2 dash at 1, which is this statement. Okay. And this is alpha dot 0 plus 0, which is 0. So, that means this P also in W, and that means W is that means this W is a subspace of the vector space V. Okay. Now, if you take the second example, second problem here, we have taken P in V such that P minus 1 equal to 1. Okay. Now, one important thing is that the additive identity of vector space and all subspaces of that vector space are same. You take a vector space V, suppose 0 is the, you take a vector space V over the field F. Suppose this 0 denotes the additive identity of this vector space, and you take any subspace of this vector space V over the field F, it will also have the same additive identity 0. Okay. Now, here you can easily see that if you take collection of all those polynomials where P at minus 1 is 1, then that polynomial, then 0 polynomial is, what I want to say basically that here we are taken all P in V such that P at minus 1 is 1. Okay. Now, what is the identity of this P2 is 0. This P2 has an identity 0. Okay. And that polynomial is not there in this S2, because it contains all those polynomials which are at minus 1 is 1. So, the 0 polynomial is not there, because 0 polynomial at minus 1 will equal to 0 only, will not be equal to 1. So, that means 0 polynomial is not there, that means additive identity is not in S2, and hence we can say that this is not a subspace of this vector space V. Or the other way out is or the other way out is you take a two polynomial, say you take 1, say you take 1 plus x square, 1 plus x square is 2. So, you take you take any two polynomials which are at minus 1 is 1. Okay. So, at minus 1 is 1 means you take 1 plus 1 is it is 2 minus 1. If you take if you take this polynomial, it is in W, because at minus 1 this gives 1. Okay. Now, you take another polynomial, say 3 minus 2x square, again it gives at minus 1 it gives 1. Now, this is u and this is v, if you add them u plus v, this is 5 minus 3x square, and this polynomial at minus 1 is nothing but is equal to 2, which is not 1. That means this element does not belong to W. So, we have shown that it is not closed with respect to vector addition, and hence we can say that it is not a subspace of this vector space V. Okay. Now, let vector V is a vector space of field F, then the intersection of any collection of subspaces of V is a subspace of V. If you take W, suppose W1, W2 and so on are the subspaces of V over F. Then if you take intersection of all these subspaces, then it will also be a subspace of this vector space V. So, things are very easy to show. You take U and V in F W and alpha in field, then since, and you have to show that this W, this Z, which is alpha dot U plus V is also in W. Okay. So, since U and V is in intersection of Wi, this implies U and V are belongs to Wi for all I. Okay. And this implies alpha dot U plus V belongs to Wi for all I, because all Wi's are subspaces of V. So, it must be closed with respect to addition and scalar multiplication. So, this implies this Z will also belong to Wi for all I, and this implies Z belongs to intersection of Wi also, because if it is in Wi for all I, that means it is in intersection also, and that means Z belongs to W, and that means this W is a subspace of this vector space V. Okay. Now, let u1, u2 up to un be n vectors of a vector space V, and let alpha i's are scalars, n scalars. Then if you take alpha 1 u1 plus alpha 2 u2 and so on up to alpha n un, then this is called linear combination of u1 u2 up to un. Okay. So, this will be a new vector. Okay, this will be a vector. So, this, and it is definitely belongs to V, because V is a vector space. So, by the closure property of scalar multiplication vector addition, this element will be in V itself, and this element is called linear combination of u1 u2 up to un. Now, we define a subset of V, which we call a span of S. Span of a subset S of vector space V is simply the collection of all linear combination of vectors in S. So, suppose S is u1 u2 up to un. Okay. Okay. Then span of S denoted by this bracket, span of S is simply the collection of all linear combinations of u1 u2 up to un. You see, you vary alpha, these ui's are fixed, you vary alpha 1, alpha 2 up to alpha n, you vary these scalars, you will get so many vectors, and the collection of all those vectors we are called as span of S. Okay. Now, span of S is nothing but the smallest subspace of V containing S. Okay. So, let us try to prove this. So what is S? S is simply U1, U2 up to Un. It is belongs to subset of V. All Ui's are from V. What is span of S? Span is S is all those U such that it is U1 alpha 1 U1 plus alpha 2 U2 and so on up to alpha n Un, such that alpha I belongs to field for all I. Now, in this theorem we have to show three things. First, we have to show that it is a subspace of V, it contains S. We have to show that it's a span of S is a subspace of V. Second, S is contained in span of S, and third is span of S is smallest subspace, smallest subspace of V containing S. Okay. Now the second property is very easy to show. You see this span is containing all the linear combinations of U1, U2 up to Un. Okay. If you take alpha 1 equal to 1, because alpha is are varying from the field. If you take alpha 1 equal to 1 and all other alpha equal to 0, then U equal to U1. So, U1 is definitely in span of S. Similarly, if you take alpha 2 equal to 0 and all remaining alpha i's are equal to 0, I mean alpha 2 equal to 1 and all remaining alpha equal to 0, then U2 will be in span of S. Okay. So, we can say that if alpha I you take as 1 for any I from n to 1, and alpha I is equal to 0, alpha p equal to 0 when p is not equal to I, then this implies Ui belongs to span of S for any I, and this implies S is contained in span of S. So, the first part is very easy to show, I mean this part, second part is very easy to show. If it contain all the linear combinations of vectors U1, U2 up to Un, so it will definitely contains U1, U2 up to Un also. Now, we have to show that it is a subspace of V. So, again you take two arbitrary elements of this set, say V and W belongs to a span of S and alpha belongs to field, and then we have to show that alpha dot V plus W also in span of S. So, since V belongs to a span of S, and this implies V is some linear combination of vectors U1, U2 up to Un for alpha I belongs to field for all I, and similarly W will be some other linear combination of U1, U2 up to Un. So, scalars will be different. So, this will be some scalar combinations. Okay. Now, you take alpha dot U plus W, alpha dot V plus W. So, it is alpha dot alpha 1 U1 and so on up to alpha n Un plus W is beta 1 U1 and so on up to beta n Un. So, when you apply the definition of standard scalar multiplication vector addition, you simply get alpha 1 plus beta 1 times U1 plus alpha 2 plus beta 2 times U2, and dot is already there. Okay. So, it is alpha n plus beta n dot with Un. Now, it is some scalar, So, we can say that it is also some linear combination of U1, U2 up to Un. So, we can simply say that it belongs to a span of S. Okay. So, we can say that it belongs to span of S, and hence we can say that span of S is nothing but subspace of V. Okay. Now, we have to show that it is the smallest subspace of V containing S. So, how we can prove it? In order to show that it is the smallest subspace containing S, you take an arbitrary subspace say T of V containing S and try to show that a span of S is also contained in T. So let T be any arbitrary subspace of V containing S. Okay. And in order to show that span is the smallest such subspace, so we have to show that a span of S is a subset of T. Then we can, then only this will be the smallest one containing S. Okay. So, in order to show that this is a subset of this, take an arbitrary element in span of S and try to show that that element is also in T. So, let say W belongs to span of S. So, this implies W is some linear combination of elements U1, U2 up to UN. And now, what to show? We have to show that this W is also in T. Then only we can say that this span is the smallest such subspace. Okay. Now, since Ui belongs to T for all I and T is a subspace, so we can say that alpha I Ui also in T for all I by the by the closure property of scalar multiplication, because T is a subspace. Okay. And this implies summation of I from 1 to n alpha Ui also belongs to T, again by the closure property of vector addition, because alpha 1 U1 is in T, alpha 2 U2 is in T, alpha n UN is in T. So, by the closure property of vector addition, this sum is also in T. Okay. So that this implies W is in T. Okay. And this implies span of S is a subset of T. So, hence we have shown that this span is the smallest subspace of V containing S. Okay. So in this lecture we have seen that a subset of vector space V, if you want to show that it is a subspace of given vector space V, we have to simply show that it is closure with respect to vector addition scalar multiplication. If it is not a subspace of that vector space, simply give a counter example which contradict either closure property with respect to addition or scalar multiplication. We have also seen that span of S, which is the collection of all linear combination of vectors in S, is simply a smallest subspace of V containing S. Thank you.